Is this follow me? So anyway, so when atoms become ions, they change sizes. Okay? They change sizes because they are losing or gaining electrons. Okay? A positive ion, and what do we call positive ions? Cations. Cations become larger, I lied. They become smaller when they lose electrons. Why do they become smaller? Why do they become smaller? They're losing electrons. What else are they losing? Energy levels. They're losing an entire energy level. If you look at aluminum. Aluminum has 13 protons. It has 2, 8, and 3 electrons. When it loses, what's the charge on aluminum? What's the charge on aluminum? Plus 3. Plus 3 means what's it going to do? It's going to what? Well, no. What does plus 3 mean? It's charges plus 3. But what does?
There's 3 more protons.
Okay, there's 3 more protons. So, but what's that plus 3 mean? It loses 3 electrons. Okay, that plus means it loses in the 3 electrons. So plus means loses, minus means it gains it. Okay, so when it loses these 3 electrons, look what happens to that shell. It's gone. The whole energy level is now gone. So one, it gets smaller because of that, right? Then secondly, you have a greater attraction between these electrons and the nucleus, so it pulls them in closer. So it actually makes them smaller. It's holding on to them tighter. So when atoms become cations, they get smaller. Does that make sense? Yes? You good with that? And up here it says it's about half their size than the corresponding metal. So look at potassium. How big potassium is as an atom, and when it becomes an ion, it's so much smaller. Does that make sense? Okay. So if you look at actual numbers, the sodium has a radius of 1.86 when it's an atom, and it's about half, about 0.95 when it's an ion. So far, so good? Okay. Now, anions, which are negative ions, they actually get bigger. They get larger when they form the ion. Why do you think they get larger? Their charge is negative. What happens to negative charges? Do they like each other? No, they don't. Do me a favor. Brooke, Claire, come up here for a second. We're going to put you over here. Okay. And Emma, would you come over here as well? You're going to remember 3 little electrons. And they're going to hold their hands like this. Hold your hands in a circle. And spread out arms width apart. Now I'm going to leave the circle and give you guys this. So it's my atom with 3 electrons. Arms straight out. Okay, now we're going to add an electron to it. So Chloe, would you come up here and join my electron group? That'd be a great song for a great name for a band, the electron group. Now watch what happens. When she joins in, they all have got to step back to accommodate her. Look what happens. The atom gets bigger. Electrons don't like each other. They're going to get as far away from each other as they possibly can. So when you add an electron or 2 or 3, that atom's going to get, that ion, it's going to get bigger and bigger and bigger because they do not want to be near each other. Thank you, girls, so much. Does that make sense? Yes? So when they become anions, they get much larger, because the electron electron repulsion. You good? There you go. Bring it back there. So a cation gets smaller when it's formed, and an anion gets larger when it's formed. So on the test, what I would ask you is something like this. I would give you pairs, and I would say, okay, which one is larger, Na or Na plus 1? Which one's larger? Sodium. I would say Cl or Cl minus 1. Cl minus 1. Not too difficult, is it? Good. And then that leads us into our, shows you cations lose electrons, they get smaller, anions gain electrons, get larger. Now let's talk about ionization energy. Okay? Ionization energy. This is the energy needed to take an electron away from an atom. If you want to remove an electron, it requires energy. Ionization energy is the term for the energy needed to take an electron away. And if you look at that periodic table, which I don't like they always do increases. It kind of bothers me, so let me draw this on the board for you. My little periodic table here. Now, we already know that as you go left to right across the periodic table, the atomic radius gets smaller, correct? And we know as we go down, the atomic radius gets larger, right? So we know about atomic radius, correct? Yes? No? Okay, good. Now, ionization energy. When you go down the column, I use IE. Ionization energy gets smaller. Why would the ionization energy get smaller as you go down the column? Why would it do that?
Because your atomic radius is getting larger.
Yes, because your atomic radius is getting larger. And where is that outermost electron you want to take away?
It's the outer shell.
The outer shell. And is that outer shell close to the nucleus or farther away from the nucleus?
Farther away.
Farther away. That electron in francium's atom is so far away from the nucleus, it basically falls off. So if here I'm my nucleus right here, and here's my electron, 7 shells out. I can barely hold on to it. Did you take it away from me, Rory? It goes there's no energy needed to hold on to it or to take it away. It basically just goes right away. Because that atom is so big. The atom is so big and the electron is so far away from the nucleus that it requires very little energy to remove it. Does that make sense? Now, what about a smaller atom? A very small atom where that electron is very close to the nucleus. Do you think you're going to get it away from me? Come on, hard that. Okay? Come on, you can do better than that. I'm not that old. Oh, come on. Put some muscle behind it, girly girl. There you go. Excellent. So you can't get the electron away from me. Well, you can, but it requires a lot of energy to do that. Because it's so close to me, there's a better bond or attraction between the nucleus and that valence electron. So the closer it is to the nucleus, the more energy is required to take it away. Yes? That is why when you go left or right across the periodic table this way, the ionization energy gets bigger. Okay? Because the small atoms are on the upper right-hand side of the periodic table and the really big atoms at the lower left. That makes sense. Yes? Are we good? So ionization energy is extremely important when we talk about reactions and things, because I can tell which one's going to react faster based on where it is on the periodic table, which one's going to give up its electrons, which one's not going to give up its electrons, and what happens when they do or they don't. Okay? You good? Now, one thing I'm going to tell you, you won't be tested on this, but you need to know. Electrons are removed one by one. So when aluminum loses 3 electrons, it loses the first electron, goes away. Then it loses the second electron, and then the third. Then it stops. Every time it loses an electron, the ionization energy gets higher and higher. Okay? Because once you lose 1 electron, you're keeping an eye on those next electrons a little closer. It's like when, I had Rambell a few years ago and I had some donuts sitting out. Someone brought me some donuts, little donut holes. And they were sitting over here and I was over here and a kid walked in and picked one up and went to a seat. I was like, what? So what I do? I took them, put those donut holes closer to me. That way, it's going to be harder to get them away. Make sense? Food. Gotta love it, right? Okay? So, ionization energy. You need to know this trend. I will ask you about ionization energies on the test. And then finally, we'll see here in a minute. Oh, a quick video on ionization energy. This talks about the second and third ionization energies. So let's do this real quick. Okay, Miss Emma? Okay.
Ionization energy is the energy required to remove an electron from an atom or ion. It measures how strongly an atom holds its electrons. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove a second electron from the positive ion. This energy is called the second ionization energy, I2. As each electron is removed by ionization, the remaining electrons experience less electron-electron repulsion and a greater effective nuclear charge. Thus, each successive ionization requires more energy. This graph shows the way in which the ionization energies of the aluminum atom increase as successive electrons are removed. Notice that the ionization energy increases with each successive removal of an electron. However, there is an especially large jump in the energy required for removal of the fourth electron. From a knowledge of the electron configuration of neutral aluminum, can you account for this dramatic jump?
Why do you think it jumps? Why do you think the first one's lower, second one's a little higher, third one's a little higher, and the fourth one goes way to the ceiling? Where's that fourth electron? It's in that 8 group now, isn't it? You've lost 3. That fourth electron is going to come from a complete outermost shell. And that means it's not going to let it go. Not too easily. Okay? So, like I said, I won't test you on that, but I think it's general knowledge you probably should have. Okay, so once again, ionization energy in groups. Okay, our final slide of this chapter, electronegativity. And we'll circle back to this in chapter 8. Electronegativity is how attracted electrons are to a specific atom. And I don't know, on the back of your periodic table that I made for you, there is an electronegativity chart. And you'll see numbers at the top. And then maybe at the bottom of your chart, I'm not sure. Top? Okay, good. Those are called a Pauling scale. The Pauling scale rates atoms from 0 to 4 on how attractive they are to other elements, or how attractive they are to electrons as well. More electrons, okay? So, fluorine is at the top with a 4. Fluorine has the highest electronegativity. It is the most attractive element on the periodic table. Okay? Electrons want fluorine. Why? It's smaller. It's smaller. The nucleus is closer to the valence electrons. It's putting out the signal that it wants electrons, and it takes electrons. These halogens are known for either stripping electrons off things or combining with themselves. They want electrons badly. Now, francium down here has one of the lowest electronegativities. Why is it low? Because it's so big. It doesn't even hardly know it has an electron out there. Why would it want more? Why would it be attractive to electrons? It's not. It is so big, it just doesn't want electrons. So this is the most unattractive element on the periodic table. Does that make sense? It's giving its electrons away. It doesn't want electrons. Electrons are not attracted to fluorine. They want to give them away. We don't talk about the noble gases. Notice how these are all blank, because we're talking about reactions here, and noble gases don't react. We good? Does it make sense? So, if you look over here on our table, then we look at, lights are coming on, electronegativities. So we call it En. The electronegativity increase, gets smaller as you go down the column because the atoms are larger, and the electronegativity gets larger as you go left to right because it's higher in small atoms. Does that make sense? So on the test, I will ask you things like, which has a greater electronegativity, oxygen or beryllium? Which oxygen? Which one has the lowest electronegativity, barium or beryllium? Barium or beryllium, guys? Barium has a lower. The larger they are, the lower the electronegativity. Does that make sense? I'm done. Stop moving. Hope it's still